the Majorana nature, which is very natural in the case of neutrino mass, you will see that the same thing happens in supersymmetry, is that you have to somehow understand that there is never just a left-handed particle, right? You said, when I speak of left-handed neutrino, why do I speak of left-handed neutrino? After all, if there is a left-handed neutrino, there is immediately a right-handed anti-neutrino, but who cares? I mean, the guy is neutral. So actually, you could say there is you could say equally that there is a right-handed neutrino. After all, who is who here? Who is more important? What comes first? I don't know. So why do I speak of a left-handed neutrino? I've been trying to emphasize this, but I can never overemphasize it, it seems, because it's sort of, again, it's there, the question remains. You want to try?
What?
Yes. Or you're going to ask a question? Sorry, no?
What? I don't know. What is the difference between taking the charge conjugate of B and say that is right-handed.
Yeah, okay. That's like this.
But is the same part? I mean, it's the same particle, just writing in another way.
Is this a number or this is a number? What is a number? Complex number or that's okay. Defining relative to each other.
At the end, we have just one. I mean, we still have 1 degree of freedom. We have just one particle.
Well, two-component state. There are 2 degrees of freedom. Remember, this is a two-component spinner. Okay.
But
it's a two-component spinner. The Dirac spinner will be 4 component. But why do I call it left-handed then? If it's equally.
But
I must have a certain convention. Okay. Why do I call this left-handed hand? Why do I call this left-handed?
The convention.
Convention. What is the convention? We had to find the convention. What is the convention? Well, the heart. In our case, the world is not symmetric, fortunately, so we could make a convention. You know, it would be very hard if we were symmetric. We would not know what to call left-handed. It would lose sort of a practical meaning, right? We would stop calling it. Okay. So what we use is the fact that weak interactions break parity. So we can define left-handed. And we decided to call left-handed the neutrino that it appears in the weak interaction with the electron. Remember, here it is, okay? This should not be, please check it if, go over it, think about it. This is so basic that this should be like bread and butter to you. Mu L bar, gamma mu El, this is our convention. Whatever interacts with an electron we call a neutrino, we decide. Anyway, that way we have of course a natural definition of a particle because we start with the conservation of the lepton number. This defines the lepton, and then we go on looking for possible violation of that apparent conservation law, right? Why I say this? Because remember, we saw that this was equal. Maybe it's better to write like this. It was equal to EC bar. Of course, EC is right-handed, if you wish. This is very important when you write ECR, to be careful what goes first. ECR is not ERC. So I had a sort of a play of words for me. In my conventions, I first have to see something in order to give it a name. In English, okay, I have to see it. So this is it. Remember the thing that drives me crazy, okay, is the notation that Weinberg uses. Weinberg uses often the opposite notation in which this is actually R is here. So it's the, and I always found it hard, okay. I'll comment on this beautiful paper that, in a minute, that I was with the effective operator. So remember, you actually knew this, or you could derive it with me. No. Mu CR. I could also write the same weak interaction in terms of the right-handed fields, of course, the anti-fields. The only thing here is the positron. And we decided to call a neutrino the guy that couples to an electron. Electron was the first particle that we saw. Positron later. So electron is sort of the defining object, right? Okay. Or whatever we call the electron, right? It's just a name. But But the convention is okay because this wireless parity. If I had both left and right states here, then it would be very hard. Fortunately, weak interaction, only left-handed state appear, or only right-handed state appear, so I can make a convention. In QED, it will be not easy to decide, right? We never talked of left and right in QED. So we call it a left-handed neutrino. Very often. In a theory with only this particle, nu EL, in the context of the quantum number of the standard model, we have a doublet, which is neutrino and the electron, and we have ER. Remember, again, this is a convention. I can always work with anti-fields. If I work with anti-fields, then I would have, and that would reproduce this interaction. I could work with a right-handed doublet, but then I would have to put antiparticles, so it would be EC and nu C. And then here would be ECL, would be a singlet. Okay. So the point in the electron, we don't speak of the left-handed electron. Of course, when there is a weak interaction, we say electron is left-handed, but we don't speak of this particle. Why? Because there is both E, L, and ER. There was always ECR. There's the same state. But there is another state, completely independent. And then, because of the fact that in this kind of picture, you and I learned that I couldn't write neutrino mass. For two reasons. There was no right-handed, there was no sort of singlet here. And I couldn't write the mass for nu. Nu is a part of a doublet. Right, so we made the prediction here that mu is 0. The celebrated prediction of the fathers of the standard model that said neutrinos. It is interesting that when the early 70s, when people started to see the sort of what appeared was a deficit of solar neutrinos. It was called the solar neutrino puzzle. I grew up with that. You will still hear these words. You must have heard of solar neutrino puzzle. That was predicted by Potencourt, one of the greatest physicists of our era, 10 years before, or more. It was still called the puzzle. I always find it mind-boggling. Remember I told you there must have been a political reason Potencourt who escapes to Russia and Soviet Union and is not forgiven, okay? It was predicted. Now, one of the reasons, of course, Potencourt was said, I believe the neutrino is a massive particle, just like any other fermion, okay? Why in the world would it be massless? Then I imagine oscillation. Then it's one thing after another that this genius envisioned. The thing that didn't help is the standard model became more and more successful, and of course this prediction became so much associated with the success of the standard model. Then a predicted phenomenon was called the puzzle. It was called the puzzle even 20, 30 years later, even in the 90s. So we said, let's add a right-handed neutrino here. Now this is very strange name, no? I added a right-handed neutrino, but this guy has no interactions with W boson. So what do I mean by right-handed? Because if there is nu R, there is also nu C L, which is C nu R bar transpose. So the reason that this name stuck, okay, and I sort of like to say it's neither right-handed nor a neutrino, because now we believe it's a heavy particle, okay, surely not some ino. There's a strong prejudice that may be heavier even than the top quark or any other particle we would associate with the standard model, even if there was another generation. And the thing, of course, is here that when we write the Yukawa interaction, we would have written, remember we decided to call this Yukawa-Dirac nu bar, E bar left-handed. We call this phi tilde, if you remember, the complex conjugate field of the Higgs. Nu R. And this through the wave leads to Yukawa-Dirac V over square root of 2 nu L bar nu R. There is a Hermitian conjugate, and a short overview of what we said already on the number of occasions. Okay, why? Because phi in the unitary gauge is V plus H, 1 over square root of 2.
No question.
Yes, please.
There's no, as you said, when we add the right-handed neutrino, which is just another particle that doesn't have any interaction, the only moment that we can say that, okay, this seems to be a neutrino and it contributes to mass when you add that Lagrangian. I mean, you explicitly mix like through the Higgs.
Right.
Mix.
No, I didn't say no interaction. I said no weak interactions. Therefore, I cannot use weak interaction to define its chirality. Okay, this I cannot do. But I just added an interaction, so it has an interaction. That's what you're saying. Yes. Mm-hmm. Now we are defining its properties. Okay, we are saying, for example, that this is a lepton. Mm-hmm. This defines its fundamental characteristic. The others, of course, are useless. It has no charge. It has no. I can't speak of other characteristic of this guy, right? It doesn't help me. It doesn't have weak charge. It doesn't have hypercharge. Mm-hmm. But fortunately, I can talk of a lepton number. Okay.
I think when you do that, you have to also add the Majorana term, which breaks the
right. Of course, we will do that. I just wanted to point out here an important thing, okay, before I do that, that there is a Hermitian interaction term, which would be nu R bar, phi theta dagger, nu EL. This will produce a mass term, which is Yukawa-Dirac V over square root of 2 nu R bar nu L. All I want to emphasize that, you see, when I have two states, nu R and this left-handed guy, I can choose which guy I want to call my particle. Okay. So when you hear right-handed neutrino, this name is justified by the fact that this guy has a lepton number 1. You agree? This is a definition. The lepton number of nu R is the same number as of electron and nu L, and therefore the Lagrangian doesn't break lepton number. Of course, the original interaction cannot break the lepton number. Now I've defined it. Now I go on and see whether there is some other interaction that breaks it, okay, but not the defining interaction. So what we call the right-handed neutrino, nu R, this is a lepton. Lepton number equal 1. Lepton number. The thing is then, when I introduce as Jorge is asking me, what I call M nu R, nu R transpose C nu R, in order to be complete, in order to write the more general Lagrangian that respects the gauge symmetries of the standard model, I am taken naturally to such a term. You see, in order not to write it, I would have now to invent a new symmetry, which is a lepton number, okay, ad hoc, postulated without any physical reason, okay. And this will be nu R dagger, C dagger, nu R star. The problem is, remember, this is where we stopped, more or less. Okay, we understood how to work with that. Sorry, not stop. This is what we talked about last time. The problem is that I have a sort of Majorana mass term, and I have a Dirac mass term, and I don't know how to work with that. Okay, even notation is cumbersome. And then the natural thing is to introduce it, you see, this particle. And this is typically done today, which is becoming a textbook notation more and more, to call new CL a new particle. Because it's a new particle, it has its own mass term, okay. Okay, they may mix, but it's surely not a neutrino one particle like in the case of the electron. In the case of the electron, this is the same particle because there is only one and the same mass term. Okay, there is no separate term for ER. Remember that Weber charge. In this case, I can speak of a left-handed again particle, okay. I shouldn't call it neutrino then because it has the thing that defines this, what will be the difference here? This is an anti-lepton. You agree? That means that it has a lepton number -1. It's just like saying I could work with an electron, I could work with a positron. We decided to work with the electron because it was always there. But the right-handed neutrino, nobody saw it, so you and I have a dilemma. Which language, which notation, which way of describing it is better? If you want to emphasize the lepton number, then call it a right-handed neutrino, but now that I wrote this, lepton number is broken anyway. So you will see that this notation is actually much more useful to us because this then is nu L transpose, CNL, NL transpose. Nu R is the anti-state. And this thing here, you will show immediately, is NL transpose C nu L. Because NL has nu R bar. Okay. Transpose. So when I have nu R bar, this is going to produce nu NL transpose, right? NL nu R bar transpose, nu R bar NL transpose. Obvious. If you're not convinced about this, okay, we can do one intermediate step if you wish. This I could have written as nu R bar, gamma 0, C dagger, gamma 0. Nu R bar transpose. Or let me put it this way, just gamma 0, nu R star. You are following me? This is just a definition of nu R bar. I introduce two gamma zeros, and this thing is nu R bar transpose. So that I have nu R bar, gamma 0, C dagger, gamma 0, nu R bar transpose. And this is from the definition that I have here, NL transpose, CNL. Using the properties gamma 0 change, you know this, okay, by now it should be very familiar. You should start being familiar like Pauli, the way Pauli matrices are charge conjugation, okay, which is just sigma 2 inside. You should start to get a feel. It shouldn't be a formal thing. Therefore, this thing that I'm banging you with, I just want to emphasize the Yukawa interaction can be written as M Dirac NL transpose C nu L plus Mn, I will now call it Mn over 2, because that's a new state N. See, this notation of N is very important. If I keep using nu, that becomes very confusing. It will drive you crazy. Because this guy is not a neutrino, okay? It's a new guy. Mn, NL transpose. Notice everything is left-handed, okay? This is sort of plus Hermitian conjugate. And this I can write as M Dirac over 2 NL transpose C nu L plus nu L transpose CNL, simply because, well, even if you have any two spinors, psi 1 transpose C psi 2 is minus psi 2 transpose C transpose psi 1. They anti-commute, but C transpose is minus C. Is symmetric. The Majorana mass turn is symmetric. The Majorana mass matrix becomes symmetric if you have more than one state. So M Dirac I can call M Dirac over 2. And then there is a historic factor 1 over 2, remember, of the kinetic Lagrangian that became very useful when we produce a Majorana spinor. At the moment this is just an overall factor that I could take out. Please here ask me if any question, because this is, you know, once again I'm really writing the thing. I want you really for you to keep it clear that we have many different ways of writing it. A particularly convenient one. You will see why I like it a lot, because I can immediately generalize it to many generations, any number of generations. Okay, this is what I like. And another convenient thing is I work only with left-handed spinners. I'm used to left-handed spinners in the standard model. Okay, I don't have to think of a right-handed one at all. But when there is left, there is right. So just a convention. So you understood the series of next time when I come, you can immediately shoot at me. I don't have to ask you this again. Left-handed neutrino, because this is the guy that participates in weak interactions with an electron. The right-handed neutrino is its buddy who has the same lepton number. But if I want to speak of a convenient way of a Majorana way of writing the mass matrix, okay, then I'm going to talk of a left-handed nu. Let's not use neutrino. They still call it neutrino. It's funny, you know, I criticize it, but I call it neutrino because it's there all the time. So when I talk to my collaborator, we call it neutrino, but it's some new heavy neutral lepton. And that takes us to the celebrated Seesaw Matrix. This is the matrix between U and N, MB, Mn. And obviously for Mn much bigger than M nu, I predict M nu is minus M Dirac squared over Mn. I predict I will induce the, when I diagonalize it, of course, a mass term here. In the process of diagonalization, this is minus md squared over Mn, 0, 0 Mn roughly.
The reason that the component is serious because we don't add explicitly the Majorana term for the left-handed component.
Right.
Yes.
Right. This was crucial. We cannot do that.
Because that breaks.
Because we break the symmetry. We are not allowed to break the symmetry. The theory, the standard model will not be renormalizable. So when you start giving up on the principle of spontaneous symmetry breaking, okay. Well, you may say, look, but what's wrong with just adding a tiny, you know, why can't I add small quantities that explicitly break? After all, this is very strange that you, and this is now, you know, this is what I would like you to do the field theory course to the bitter end. You should take my word for that. There is no explicit breaking. In other words, okay, let me try to explain the fundamental principle here, because we often talk about the predictions of the standard model. And the predictions of the standard model are based on the following. So predictions of the standard model are based on the fact that the standard model is spontaneously symmetry breaking version of the SU2 cross U1. So anyway, I'm speaking of the electroweak theory, gauge theory. Spontaneous symmetry breaking. That means no explicit breaking whatsoever. Okay, so people often imitate that. For example, I could have forbidden here, imagine this important thing that defines the seesaw mechanism. I could have said, I can now postulate in analogous manner, let's now postulate lepton number. After all, I just postulated a gauge symmetry. It's not that it was there. I decided, I said, okay, let's show Weinberg, Salam, whatever, X. So I postulate lepton number. If I postulate lepton number, then I will get that Mn is 0. And then, of course, I will predict that lepton number is not violated, obviously. Okay, there is a funny tautology here. Okay, so I will claim this is a prediction. You cannot see neutrinos double beta decay. It sounds like a prediction, you know. You may say at the first glance, well, this is similar to what the fathers did here. Or, for example, I could predict SU2 isospin symmetry. This wouldn't be very smart, because then I would predict that M proton is equal to M neutron. And then neutron wouldn't decay and so on and so forth, okay? So this wouldn't be smart, okay? So you say, aha. So what's the difference here and here? Why is it that I would call this a prediction? It's not a purely philosophical question I'm raising. It's a practical question. It's a fundamental physical question. I wouldn't call this a prediction. Because remember that when Maurice Goldhaber, he likes to tell this story, he used to like to tell this story, wanted to measure proton lifetime, people told him, but proton can decay because it's stable. Oh, how do you know it's stable? Because of baryon number conservation. And there people, what they did, they assumed the baryon number and they called this a prediction. So why would I call this a prediction and this not? And the point is that if I add even a tiny breaking, all hell breaks loose. The theory stopped existing. We cannot compute anything. The theory is not well defined anymore as a quantum mechanical perturbative theory that allows you to compute physical scattering process and whatever else you want to do. So when I hear no explicit breaking, not even minimal, when I postulate a lepton number, you can say, okay, I will postulate almost lepton number. In other words, nothing forbids me to go away from this conservation law here, from this image. I can move continuously without losing anything. The theory is equally calculable, equally predictive, equally good. Therefore, this particular point of exact conservation law is not a special point. This is a special point, the theory of exact SU2 cross Yuan gauge here. It's a special point because you have to stay on that. You can't move even infinitesimally, okay? This is what defines it. So in other words, gauge symmetry, and this is not surprising that there is a difference. Gauge symmetry is a dynamical principle. It has to do with the way the world interacts with gauge principle. So this is what sets it apart from a global symmetry. Global symmetry is just some bookkeeping. In other words, saying that the isospin is a perfect symmetry, or saying that isospin is a pretty good symmetry, is equally good or bad, if you like. I can break isospin, which I do. It's still very useful as a bookkeeping. You do it all the time. You classify all the breaking thing proportional to the tiny thing, okay, which to us we know is the difference between up and down quark masses, okay, this tiny difference produces these effects. And it works quite well, you know, pions have almost the same mass and so on and so forth, okay, so pion decay processes of kaons and so on. But the gauge symmetries I cannot touch, okay. So the only theories that we have are exact gauge symmetries. Or spontaneously broken. But that's exact, it's just the vacuum decides. Right? The ground state decides, forces us to live where it seems not broken. Okay. So what we said here, you see what we do, we have diagonalized this matrix because we said that there is this particular matrix. Neutrino n, because it's easy to see that m nu n, when it acts on epsilon 1, is roughly mn, not epsilon, let me call it theta, I will see why. Theta 1, if theta is m Dirac over mn. And the same matrix, when it acts on 1 minus theta, produces minus md squared over mn, 1 minus theta. If you wish, analogous way of saying is that the unitary matrix 1 minus theta, which actually orthogonal, everything is real, diagonalizes the matrix. Remember how I argued, if n was complex mn, I would just change the phase of the field. And so in the case when it's all real, I simply have that O transpose mn m nu n O is the diagonal matrix, which has a force minus md squared over mn 0, 0 mn. Now what emerges immediately, that if you know nu and n, remember the thing that I kept emphasizing in the standard model, what is the great success of the fermionic mass Lagrangian in the standard model? If you wish, the celebrated Weinberg's 1967 work is the following, that Yukawa coupling, and it was Yukawa over square root of 2, was when we normalize it, m fermion over mw. So in other words, when you know m fermion, you can predict the Higgs decay rate. So knowing the masses, okay, this is what it means to probe the origin of fermion masses, okay. You can then predict immediately the decay rate, and you computed this in the homework. So you find out that gamma h going to ff bar is proportional to mf squared over mw squared times mh, and so on and so forth. So you may ask an equivalent question. Would the seesaw mechanism, that's the analogous thing? Otherwise, why talk about it? In other words, now, of course, the input is not one mass. Today, we would have to measure two masses, and we should try to understand how. There is not just one neutrino. There are two neutrinos because of the Majorana thing, right? There is light and heavy. There is one charged fermion, but two neutral fermions. And the answer seems to be yes. If you say that you know m nu and mn, this is the equivalent of measuring m fermion. You can predict m Dirac, which is minus m nu mn. Forget the sign, we can talk of the absolute value. When you know m Dirac, you can predict the Higgs decay rates. Or whatever rates are important, we'll come to that. Or maybe we can comment once again immediately. After all, we showed, because of the mixing here, because of this mixing, because of the fact that you have to rotate the physical states, we found out that this induces the interaction g over square root of 2 theta nl bar gamma mu el W mu plus. Notice that here, this is the homework problem that you're doing. Notice that here, the notation left-handed is becoming useful again. This is how the new guy interacts with the W proton, interacts with the left-handed interaction. When I, of course, specify the electron, and I want to specify the electron because this is a particle that I know and love, not the positron. In the anti-world, they would have spoken of the positron and so on, right? If you meet someone from the anti-world, we should be very careful. We would have to discuss with the person from the anti-world, right? Don't shake your hands if you know, if there is a possibility that someone is coming made out of antiparticle, right? We would have to avoid that. Okay, he or she would annihilate before touching us, but anyway. You were no, I thought you were going to ask. So you see, for example, if you notice theta, and notice that the theta, what was theta? Was MD over Mn. You see, this is the knowledge of MD. You would immediately predict the decay rate. This is what you are computing it, right? Computing now into E and W plus. So if I give you MD rack, and that means if I give you mu and Mn, I can now, it seems that I could do what Weinberg taught us he could do. That you give him the mass, the input, I can now predict associated physical processes and test the mechanism. It seems. In order to know whether this works, we have to go now, we have to speak of generations, okay, the way we did in the charge fermion case. So I want to generalize this for briefly to extra generations. Let's imagine that there are n generations. So from a state which was erased, from the Yukawa-Lagrangian, which had a term which was MD. Remember, N L transpose C nu L. Remember, this was the starting point. Let's generalize it. So in other words, this we want to generalize, okay? This defining term into N L I transpose, there is always C. I'll stop writing it. M Dirac Ij nu Lj. It's not a matrix. And I and J go over generation. That's a generation index. Agree? Okay, this is the definition of M Dirac. This is easy to see immediately that this is equal, if I commute it, to nu Lj transpose. This becomes C transpose, but it has a minus sign. Okay, so let me write. Minus C transpose MD Ij N L I. You agree? I commute it, I get a minus sign. This will make C transpose because this goes first. And I have my MDIJ, but this is nothing. This is plus NLJ transpose C, and this is M Dirac transpose JI NLI. So this I can write as 1/2 N L transpose C M Dirac nu L plus nu L transpose C M Dirac transpose. I write in the matrix form as we always do, and then I've introduced states nu L is nu 1 to nu n. Left-handed NL is N1 and then left-handed plus 1/2 N L transpose C M N. These are now matrices NL. Okay. In the case of one generation, there was one and the same M Dirac. Of course, I couldn't distinguish Dirac from Dirac transpose. In the case of more generations, it's Dirac transpose because of the interchange of nu and n. You agree? Matrix going to a transpose. The factor of half, I'll remind you at the end of the lecture why there was a, once again, I'll remind you. But actually, I'm going to send you some extra notes, and I'll tell you what to read if you want to read in the books, and I'll send you some of my handwritten notes of this. That should help. So in other words, the up to a factor of half, the neutrino mass matrix up to a factor of half is 0, and this is nu n, so this is n nu I call md by convention, okay? This is just a convention, what I call md. What is important that if this is md, this is md transpose, okay? This now is not a convention anymore. It's okay once we are clear what we mean. Mn. Now these are matrices. So what we do when we have these mass matrices, what we did for charge fermions, we diagonalize them to get the physical states. So what we want to do here first, we want to block diagonalize. Notice an important thing that this is a symmetric matrix. Because this is symmetric. My random mass matrices are symmetric. Why is it symmetric? If I interchange them, I will get minus C transpose, but that's C. The same way that it took us from Dirac to Dirac transpose, when it's the same state, it will be symmetric. Picks up a symmetric piece. But remember what you and I learned. Any matrix can be diagonalized. UMV dagger can be made diagonal. When the matrix is Camitian, well, let's write here U dagger D V is N. From here you find out immediately that V is U when M is Camitian. This is always U. Camitian matrix is diagonalized just by unitary transformation. And you will find that V is U star when M is symmetric. Which I call a little bit, I think in my notes, I think I write that U transpose M nu n U is diagonal nu n. What I call U or U transpose, okay. This just boils down to the fact that it's it has to, the diagonalization has to preserve the symmetricity. So this U in the case of one generation, if you remember, we knew this U was the O I written before. I don't know if you wrote in your notes. And there was one generation, U was O, so one generation. And that I called 1 minus theta, theta 1 for one generation. For n generations, this immediately generalized. We will generalize it to 1. In general, this is complex. Y dagger and not transpose. This is a definition of my, this must be unitary, this matrix. Matrix is unitary. We can check immediately U dagger. U minus theta dagger, theta 1. Therefore, U dagger is U dagger 1 plus theta dagger theta 0. Do you see? Zero minus theta plus theta. I can be explicit if you wish. Here minus theta dagger plus theta dagger, and here 1 plus theta theta dagger. We will do it in the approximation of small theta. We are anticipating. Remember the theta was small. What was theta? Was m Dirac over mm. And it became a square root of m nu over mm. So I'm okay. So I plug this in, and shall we do that? So I have to compute U transpose Mn U. What is U transpose? This is a definition of U. Forget n equal 1. This was just a feeling what to get. Okay, so you understand what I'm doing. I'm going to assume that theta is small, so I'm going to do everything up to the second order. That's what I need, because this is what I did with one generation, okay? I found the eigenstate only up to the leading order. Remember, it was very messy with some square roots and so on. So n justify means here, okay? Let's say if we get the right n, that justifies, you know, the assumptions we are making. I'm assuming that n is very heavy, so if I am okay, it should all be self-consistent, and I should get a small m Dirac. Do I want to do this? Well, let's just illustrate what we get. All right, let's write it. So what is U transpose? 1 theta star minus theta transpose 1. You don't think I'd like to check my notes just to be sure that I have the right U transpose? I think I do. Okay, so here is U transpose. Okay, so I need this to start with. So when I act here, what do I get? I need your help now. I don't care if you're hungry or tired. I need your help. Okay, 1. What do I get here? I get minus theta transpose m Dirac. Correct? First time first. First time second will give me m Dirac transpose m Dirac transpose minus theta transpose n.
It's not
Mn.
theta dagger? It's not theta dagger?
This is U transpose.
Okay.
U dagger was here. Let's forget about U dagger.
Okay.
This was just checking that it's gonna. We are doing n generations. Okay, I will erase this so that we have as little of unnecessary stuff. I didn't even have to tell you that the symmetricity of the matrix guarantees that it should be U transpose here. When it's Hermitian, it has to be U dagger. Okay, I keep this. This is fundamental. Okay, minus theta Mn, am I right? Okay. Then I'm here. Theta star gives me 0. I get here. Am I doing this right? Second times first. You give me M Dirac here. Am I right? Kind of suspicious, but well, I go. Then look at the 2 times 2. I'm doing for small m Dirac or large Mn. So this is roughly Mn. Okay? Plus a small contribution here. I'm doing the leading term. This should be multiplied by this. So let's write it. It's going to be easier. 1 theta dagger minus theta 1. So what I have that U transpose mu and U, what do I get? This. Then I have to multiply, look, the first piece will remain the same because this is obviously small. So what we'll get here minus theta Dirac MD. Okay. Now I have to diagonalize it. So what is the second piece? Theta M Dirac theta dagger. This is small. This is already theta squared times M Dirac times this. Times this. But this has to be 0 by definition. But let's write it. That will be M Dirac transpose minus theta transpose Mn. I don't want to move here. Once I define this quantity, I should be okay. And the second piece here is Md minus Mn theta. Even the order is, I have to be careful about the order. I hope I'm keeping the order correctly. Because you do that. And then look at the last piece. This is small, M Dirac is small, multiplying a small number, so it stays Mn. So this is okay. I'm assuming that this is more roughly, so I should write like this. This must be what I would call mu 0, 0, Mn. This is my first step. I am just diagonalizing blockwise the thing. Then later on I can worry about these mass matrices. This is now easy, okay? This lives in its own world, okay? This lives in my world, and I can diagonalize it and introduce the Cabibbo-like mixing, Montecorvo mixing, let's call it. So the first thing I learned, that this must be 0, M Dirac must be equal to Mn theta. Okay, this defines the mixing matrix theta. The same as before, but now these are matrices, okay? I'm on the right track. Previously they were just numbers. Okay, theta was Md over Mn. Now please, keep the order. If this is 0, this better be 0, otherwise, I just leave and let you go ahead. Okay. We can check it, but I'm gonna feel lousy. M Dirac transpose is theta transpose Mn because Mn is transpose. It's symmetric. You see, when this is 0, this is also 0. I have because this had to be 0 and this had to be 0. So I'm okay. And I predict, let's write it here, I don't need this anymore, that the matrix U was defined. I introduced a mixing, theta dagger minus theta 1. It's easy to see that if you write this theta, this will be theta dagger to be unitary. Okay, you could have written theta 1, theta 2, and you will use that unitarity. Okay, you could have invented this easily. There was not a big deal here. So what I predict here for M nu, now I have a prediction. So I have one more prediction that M nu, the matrix, induced matrix by these heavy fields, is, what is theta transpose? So M Dirac transpose is theta transpose Mn. Mn is symmetric. Therefore, M Dirac transpose times Mn to the minus 1 is theta transpose. This is an equivalent equation. You can write as many equations as you like. You can solve this. For example, from here, I can write that theta is Mn to the minus 1 M Dirac. Mn minus 1 must be on the left. Keep the order, please. These are matrices. Okay. So from here, I get that M nu is minus sign. This is okay. We had a minus sign in one generation case. And where am I? What do I need? Theta transpose here. So this is M Dirac transpose 1 over Mn, or Mn to the minus 1. I will write sometimes this way, sometimes the other way. This is the celebrated Zito formula generalized to more generations. When one generation, this is just a number, so it reduces to the case. For example, when M Dirac is symmetric, you would get the one generation result. So this is the Seesaw formula. And the way I got it was assuming that Mn was large. It's not that I did something miraculous. I just got the form. But there was an assumption built in that Mn is large. Okay, that's not surprising. We could have guessed this. All I needed was this precise form. And let me show you why. Because remember what I said, if I can predict M Dirac, I can compute anything. I'm as good as Weinberg. You know, you and I can do that. We can beat him. He didn't do that, okay? So let's try. Let's see if he is good. So from here, look at M Dirac. I can write M Dirac. Maybe I need a square root of I because somehow, okay, I'm guessing the form. Okay, there is an educated guess here, but you can. Actually, let me leave this empty space here. Notice that if you plug in this here, you will get immediately that it works. In other words, it seems that I can predict M Dirac. Remember, for one generation, M Dirac square was Mn times M nu. Because from here I would write that M nu, what would be M Dirac transpose? That would be I, square root of M nu transpose, square root of Mn, but these are symmetric matrices. Square root of Mn, 1 over Mn, square root of Mn, square root of M nu. And there is twice I, so I will get the minus sign. Mn, 1 over square root of Mn gives me 1, and I get desired result. So it seems that I am doing okay. just go and say, okay, we stop at this point. Why should we go on? We achieved something very important, and I'll give you the Dirac matrix, okay? And you can predict in generation space this decays of N decaying into W, Higgs decaying into N decaying, whoever is heavier. You can do the same thing that was done in the standard model, okay? Or so it seems.
If N is of the order of the, is of the order of the 10 to the 3 gigaelectronvolts, yes? N?
Well, that we got. Remember, if M Dirac was the order of the charge lepton of the electron mass, in that case for one generation, we got the number which we liked because we could hope to produce it. But also then we were worried because how in the world you're going to produce it at a very tiny coupled VW. So remember, we actually failed. We came up with a prediction that there would be natural to have a heavy particle that you could go and study in the collider, and you are studying its decay properties. By the way, the homework problem is the 3-body decay. Did you look at it? One part is N decaying through the 3-body, just like Muon. That's a bit long. So I say it immediately. If it becomes too long, okay, you know you know the result, right? Because you know the Muon decay. It's just like Muon decay. You have a new W prime. So by analogy, you can write the decay rate. If it gets too long, I don't know how much stuff you have over the weekend, so you decide, okay? I wrote it there. You will not be punished. Let's say you'll get extra credit if you manage to compute it. And this can be looked up, right? There are books that study the Muon decay. This is not a new calculation, okay? But you know, getting the matrix element square, it's like a Fermi theory. It's a bit long. Now, before we celebrate here, let me show you something. Suppose I put something. This is not 0. This is some O. Okay? What will happen? Help me. M Dirac transpose will be M nu. This will be O transpose. You agree? And I would have O here. So what I would get is minus square root of M nu. This gives me 1. By definition, O transpose O square root of M nu. So if O transpose O is 1, I get I get the right result. Plus there was a, what did I write? And Dirac was, it was minus that, so there will be a plus sign. Remember, it was minus. I'm just checking whether I... So you see, notice that M Dirac has an ambiguity. In one generation case, this is not very ambiguous, right? O square is 1. Maybe there was a sign ambiguity that had written, I don't care. But notice what happens with N generation. I get a serious problem. I cannot determine M Dirac. Any M Dirac that differs from what we liked before by an orthogonal matrix is as good as any other. This is the ambiguity of Seesaw. Now notice these are complex matrices. So there is ambiguity by the orthogonal matrix. O complex in general, not real. There is no, I can't assume reality here. You know, these are now matrices. I can't make them all. I don't have enough phase freedom to make everybody real, okay? I can start by making Mn real by redefining N fields. Imagine that I can do that. M Dirac, of course, then I've used up the freedom. And by the way, notice this. If you have never seen that the complex orthogonal matrix can be arbitrarily large. When the, is this clear, please? When you of course, you all know You all know that unitary matrices and orthogonal matrices, we were always used with real orthogonal matrices. If O is real, then O transpose O is 1 gives me O is cosine, sine, minus sine, cosine. So the elements are never large. The elements of orthogonal matrix are less than 1. Or equal. If you have a unitary matrix, U dagger U is 1, then you will find out that U is C e to the I alpha, S e to the I beta, minus S e to the minus I beta, C e to the minus I alpha. Maybe you stick in another phase, whatever you do, same thing is there. And that's simply this property. We'll give you the sigma elements. So they are less than 1, or at most 1. Not anymore for orthogonal complex matrix. Let's give an example. Okay, forget the unitary here. I don't know why I needed to. Let's just talk over. If it is complex, I think this is orthogonal. Let me see. CH of, how should we call it, eta, SH eta, CH eta. Shall I put a sign here?
No.
Maybe just like this is better.
Yes.
Is it true?
It depends on the metric.
No, O transpose is 1. O transpose we will. Let me put a sign here just to. Okay, plus or minus. I remember. So O transpose will be CH eta minus plus SH eta, SH eta, CH eta. So what is O transpose? I don't like this.
Cos square plus sich square.
I would have to multiply this by this. Wait, this by this. I will get CH squared plus. Maybe I don't like that. What if I try this?
Up. Yeah.
Let's try this. If it doesn't work,
I think
well, we won't go into. We'll have to figure out. Let's try this, okay? This will be. What would I get? No, this is not good.
You get cos minus C.
This would look good.
O transpose O with the previous one would be 1. Quite easy.
Sorry?
The other way around is making it easier.
Put a
With the minus
sign
there,
here.
Yes.
But keep I.
No, without I.
Put a minus sign here.
Yes.
That's what Vasif is saying. I don't think so, because this will be minus, and this will be plus.
Oh,
Then you get plus again.
No.
And then I will get, this I don't like. So let me try I,
Yes.
You get 1.
and okay, plus or minus I. Then I will have minus plus I, and this will be I.
Why minus plus?
The O transpose. If it's plus O.
Plus minus.
No, it's okay. If this is plus minus when I take the transpose,
There's no Hermitian conjugation.
It's just
there is no
transpose.
Hermitian conjugate.
It's plus minus.
Okay, plus minus. So what do I get? The first piece is good. It gives me CH squared theta minus H squared theta. This is 1. Good. The second, this times this. Would be good if I put a minus sign here.
You need a minus.
So let's try this.
And it's 0. Yeah.
Then it's good, I think, right?
Yes.
and then it's good. You can do it. So you see, but this can be infinitely large. So among other things what we learn, you see a tremendous problem with the seesaw mechanism, okay, which is hidden under the rug. Now look what people do. Okay, and this is somehow a, this hurts me. Look at the cheat that people do. But this is an ambiguity, we can live with that. We are learning that M Dirac, in the one generation case, M Dirac was small. So you see, I justify the assumption I made. How did I start in the case of one Dirac? I assumed M meant to be large and everything was consistent. I went back and I found that M Dirac was a product of this, and that was much smaller than Mn, okay, square root. But then I learned I can produce the guy because then it couples only very weakly with the, because theta, which I raised. Did you write what theta is, matrix? I think it was Mn to the -1 M Dirac.
Yes.
Yes.
So, now I can do the following. M Dirac can be as large as I wish. This is literally what people do. And I hope you and I will, you will agree with me that it's crazy, so when you hear some guy speak like that, you should get upset. Because he said, look, I did all of this assuming that Mn is very large or that M Dirac is small. I diagonalized it way, I got the seesaw mechanism, and I said proudly, I know why neutrino is light. I have a new theory, but now I'm saying that O is very large, that M Dirac is not small. So why is neutrino light? Because there is accidental cancellation of huge numbers. This is huge, but because of the structure they cancel and I get a small number. But this sort of is crazy because I diagonalize it by assuming that this was small. The only reason people do that because now if M Dirac is large, this can be very large and I can produce N. It's not a seesaw picture. It's not even correct what I've done because the block diagonalization made sense only if this was very small. So I would consider this a failure of the, but in principle, though, you could say, I don't care, it's ugly, it's stupid, it doesn't make sense, whatever you say, okay, I don't care, you know, beauty, elegance is for the tailors, you know, I'm a physicist, I don't, well, whatever. I want to tell you that we should think better because, you see what I'm trying to do here, because we are going a bit away from the standard model. I'm arguing that we are now in the same situation. I want you to understand that the standard model took us today to where they were taken 50, 60 years ago. They had weak interactions, they had an effective theory, and I also can speak effectively the way Weinberg did with this 5-dimensional operator. But the task then was to find who the culprit was. What was the origin of these weak interactions, and it opened the window to new physics, which is, the rest is history. And this, I would argue, is the task today, because this is the only place when the standard model failed. Okay, I've been arguing this for years. That this is the window, not what other people, not naturalists, not strings, whatnot, okay. We have a very simple and clear task. We should find out a theory of neutrino mass, or the theory if you are lucky, which means that if it is good, for example, I should be able to predict M Dirac and go and measure in the experiment. Here I failed completely. Or how to say, I failed to fail. I can't fail. Whatever number you get for M Dirac, I said, yeah, it's okay, because this, I don't know, I'll fix this, okay? So, no, this is, you know, a good theory. By the way, it's not easy to write. A good theory, I would define the one that makes clear predictions, okay? Up to now, I only managed once to write a good theory that failed, okay? I can tell you about it at some point, okay? I'm also writing something these days, or a number of years, which I hope will fail if it doesn't work, at least. I like to I want to live with my prediction. But I think anyway, from the point of view of us, the students of the standard model, which means the students of the neutrino mass, we have to do better than this. Okay. Before I finish for today, which I wanted to tell you a little bit about this physics that can do better. No. Let me then finish on the technical mode. You see, today it's basically technique, very little physics. Very important. So I want you to remember here, this is Seesaw ambiguity, and this complex means O can be not only arbitrary, but arbitrarily large. I can't even justify, you know, I assumed it was small, but I can't justify it. Okay, in that sense I feel that this interesting failure when I went from 1 to already 2 generations. You see, I failed already in 2 generations, okay? It wasn't a some fancy thing of having many mixing angles and so on. With one mixing angle that I made complex, it became cosine hyperbolicus. Now, remember I've been arguing that, I've been showing you when we write down the effective series, by effective theory, what we mean, normally I've been using this language, I spoke of Fermi theory as effective theory. It's effective in a sense that it has a higher dimension, so it cannot be in the original normalizable Lagrangian, right? Fermi theory goes into that category, this thing, G Fermi over square root of 2, written psi bar psi squared. Or why don't we write psi bar gamma mu psi? Actually, it's a little more complicated. Or why do we write this even better, that this is G Fermi over square root of 2, even better, J mu. We can call it the weak currents, okay. This is the effective theory. And the currents, because of this, have dimension 3. This having dimension 6 implies the G Fermi is 1 over lambda squared. We found out that if we exchange a heavy particle called W here, we can reproduce the thing as long as the momentum exchange is very small. Okay? You will often hear this language. What we say in physics is that we integrate W out, which means the following. Imagine that in the, after all, how do I get this interaction? Okay, I have to find the propagator, then take the momentum going to 0, but I can do it simpler. I can start from the beginning with momentum going to 0. That should be easier. So how would the Lagrangian look like? There would be 1/2 Ma. Let's imagine some gauge boson. So in other words, I want to generalize it. I have some gauge boson A that couples to some current mu. And I have a massive gauge boson and then this interaction, G. Remember the mass of the gauge boson goes with a plus sign, the so on and so forth. A mu, we said it many times, J mu. This is how it would look like, okay? What we did, we wrote the whole kinetic energy, we found the propagator, wrote the propagation, and then take the momentum to 0. Why don't we just take the momentum to 0 to start with? Then the Lagrangian, very simple, it has only a mass term. The guy is so heavy, it's inert. It doesn't move. Therefore, the equation of motion is not a really equation of motion, it's just a constraint immediately, right? There is only the derivative with respect to the A mu, which gives me ma squared A mu equal to G J mu. Or maybe the key. So what do I get? So in other words, you see this field actually doesn't exist anymore, it's just a constraint. I can immediately eliminate it in favor of J mu of the current. And what I will get an effective interaction, which would be what? 1/2 ma squared. What is a mu? Is g squared, J mu divided by ma to the 4th. Correct? Minus g J mu. What is a mu? Is another g, so I get g squared, J mu over ma squared. What do I get? I get minus 1/2 g squared J mu ma squared. I get immediately Fermi theory. This is much simpler, okay? So in other words, the reason I'm saying for 2 reasons, okay, that this is an easy way, this is a good check to see whether you've done something right when you know, computed a complicated propagator in a complicated theory and then look at the low energies, okay, you should get the same result by simply integrating the field out. So we say that we integrate out a mu, right? It was integrating out. We solved for it, okay? And we got the effective interaction, which is current times current. And of course, what we do that, there is no propagation anymore. We just pinch this, okay? And remember I said that in the case of Seesaw, I could see the seesaw as neutrino entering, becoming n through the Higgs. There were some Yukawas here, right? And propagating n. And the propagator of n is k / minus mn. This coupling was m Dirac. This coupling was m Dirac. Sorry, Yukawa Dirac. And I will get from here Yukawa Dirac square v square in the vacuum phi 0 is v divided by mn with a minus sign. So I could reproduce the same way. And also, of course, once I pitch mn, I see that it's so heavy, it's not even propagating. We are getting effectively Weinberg's operator. This is what we already done. I don't want to talk about it now, but I said the simplest thing would be from my Lagrangian, nu n, which was minus m Dirac over 2, I wrote nu n, how did I write it? Minus m Dirac nu n plus n nu. Minus mn over 2 n n. This is how it would look, right? Which is simply minus m Dirac nu n with 2 ways. It was the same thing. So if I take the derivative with respect to n, I will get minus mn n minus m Dirac nu equals 0. Notice that n becomes m Dirac over mn times nu. The same way that a field here was solved for the source is coupled to, the same way this heavy guy could be eliminated. And I would get minus m Dirac, n is, so it becomes plus m Dirac squared. Why does it become plus? That I'm not so happy about, not really, I don't care about the sign. And n is m Dirac over mn. So this becomes nu minus mn over 2, n is m Dirac over mn square nu. Well, if I write the mass term, sorry, that should be plus. This was the mass term, okay. The Lagrangian is minus sign. I don't know why I had to write the... Anyway, this is correct. This minus sign is correct. And I get minus 1/2 m Dirac square over mn nu. Notice that I'm using symbolic notation, nu by this I mean nu transpose C nu and so on and so forth, okay? This is not so important, it's a Lorentz indices, okay? I'm simplifying it. You can do this carefully, okay? I'm going to have a homework problem. I think it would be nice to check it for n generation, so you get a feel what it means to integrate the fields out, okay? And if you're right, we should get the same formula, this complicated way of arriving. You see what I did? I had to do all kinds of gymnastics to arrive at that formula, which was mn. I found that nu was minus m Dirac transpose, remember? 1 over mn m Dirac. It should come out when I integrate my fields out. It would be good to see it. So that even if all of that mess, you know, at the end, oh, I don't know, I would have done it, I should just get it by repeating this, okay? So I'm just giving you a hint so that you can do it in the homework. Oh, it's time to wrap it up.
It makes any problem design for the propagator.
What do you mean for the, sorry, the propagate? There is nothing propagating here. This is the, there's nothing anymore propagating. Nobody's propagating anymore. I'm taking this infinitely heavy.
Okay.
I'm getting rid of this guy. This guy doesn't propagate. There is no real equation of motion for this guy. The guy really doesn't exist, if you wish. When you go to the limit of the guy not propagating at all, it's equivalently sending the mass to infinity, strictly speaking. For you, that guy stopped to exist. In that sense, if you want to just look at the effective theory, then Weinberg operator is better than all this complicated language. If n is so heavy that you are not going to produce it, then don't even write these complicated things, okay? If W is so heavy that you and I are not going to produce it and we won't have the theory, write the Fermi theory. That's the correct language. So effective theories are good language when you don't have a fundamental theory behind. If you think you have, then of course, n will not be infinitely heavy. Then you and I are going to study how to produce it. And we don't want to produce it by this trick, which is against the whole seesaw mechanism, right? We want to have the theory of the right-handed neutrino. We want two things out of the theory, or three. First, that it predicts its existence. That's a good theory. Not that you put it by hand. Second, that it predicts its properties. Third, that I can then disentangle C so that I can solve for m Dirac. Okay. So here the sign is actually what I like. The sign of this mass with a minus sign. I didn't worry so much about the sign. By the way, I can take care of this by multiplying this by I. Let's redefine the phase of nu. I kept it for the time being. I didn't speak on mixings, okay? And just one last comment. We are finished here. This factor of half, remember, it boils down. When at the end it boils down that the Lagrangian is I, nu bar, gamma mu, d mu nu. After all this, you know, song and dance, it boils down to this, minus m nu over 2 nu transpose C nu plus commission conjugate. This is what I got. With m nu, I got minus m Dirac square over mn. But if this is sort of so heavy that I don't see it, just write this. And then we introduce the Majorana state, which we call nu m, which was, by the way, this would be left-handed, sorry. Forgot completely to write, there was a helicity, chirality in question. So we define nu L plus C nu L bar transpose. And then you proved in the homework that I nu M bar gamma mu d mu nu M is twice I nu L bar gamma mu d mu nu L. Twice because actually there are two fields inside, which is the same field. This is the same field. It's just a complex conjugate guy, the same field inside. So you get a factor of 2. That's what you've done. And this is why there is no factor of 2. If you write like this is not the mass, this is m over 2. Because the mass is what is defined from Dirac equation, because then we will get 1/2 mu Majorana gamma mu d mu nu Majorana. Bear with me, just this. Minus m Majorana nu m bar nu m. This is what you've shown in your homework, okay, with the factor of 1. And then you get the usual Dirac, like propagated Dirac equation. So this is the mass. Because you will get that p slash nu m is mm. Well, let's just write it m nu m, which means that p squared is m nu squared. So this is the mass properly normalized. Okay. This is why factor of 1/2. Okay, just remember that. There's nothing mysterious about that. Majorana spinor is sort of double of that kind. So. Okay, this would sort of wrap it up here. What I had to say about what we could call the new standard model, okay, the so-called Seesaw picture of the standard model. I've basically have nothing more to say. So I hope there'll be more questions. Next time we'll talk a little more about what could be this physics beyond the standard model. But there's a candidate behind the what we talk here. I can. Any questions for general public?